Okay, in this video, as part of our course G04 mutation detection, we're looking at screening snips and indels with VCF tools and VCF utils.pl. So this demonstration video will cover how to implement this directly on the server. We note that this is .pl because it's the Perl script that's operating here. And that will mean we can identify more precisely the true snips, distinguishing them from the ones that may not be actually real. So what we'll do is use bgzip to compress our VCF file output like that. And then when we're trying to read them, we can use gzip to decompress that in this manner. So use gzip.decompress. We'll decompress it temporarily to send output to a tool or to the screen. And then a second task we need to do is index this with Havix. So the Havix is a type of indexing for VCF files, which will mean that it's more easy to look at that further. We will use is VCF tools function called isec, which gets the intersection of the input from Freebase and the input from VCF tools, subject to certain criteria listed there. So look for the number equals 2 for each variant that they're present in both files. That one file is put as output, that we're creating VCF output, and this is the name in.merge.vcf. We'll also use VCF utils as well, which creates a filter with a depth of at least 10 coverage of at least 10 with at least 6 alternate alleles from our merged VCF file to create a filtered one. We can then apply VCF tools stats function to get the TI/TV ratios from that. So we're using getting the stats function, which produces a long list of output, and then grepping that to get the TSTV or TI/TV ratios as they're also known. And that will give us things like this. So we'll be able to estimate the TI/TV ratios for all the different options, which you'll find may vary a little bit depending on the tool and mapper that's being used and the technology, which is Illumina here for ER99 and ER63 is Nanobore. Then we'll be able to look further at the headers in our VCF files, and you can get them using this grep function to get the hash lines containing a hash from there, and they contain things like the DP value, the number of observations of each allele, the alternate allele observation count for RO and AO, containing the different types of information. We can also grep our files to estimate the number of mutations per category, without those being insertion, deletion, snip, and more complex variants. What we'll find is that the output we get across different technologies and snip callers and mappers may differ. So if you look at Lumina here, you might find Minimap2 and BWA tool give similar outputs, but not the exact same. And we see there that the TI/TV ratios are somewhat bigger for VCF tools here. Whereas for the Nanobore data, Freebase may struggle to accurately interpret that. We see a different pattern of mutation coding there for that compared to VCF tools here. And what we'll need to do is use bgzip and Havix to index our VCF that we're looking at, and that will mean we can then assess the consensus between the two, which arguably contains a more accurate subset at the end. And what we can do is also use that same function, VCF tools isec, to, on the next slide, to get sites in the first VCF that are absent in the second one. So if we have VCF tools isec for the first file and the second file, we can have C get the snip in the first, absent in the second, and the output is VCF. And then we can reverse the files around to get the ones that are absent in the other file. So when we try this for the different files given by these commands here, we'll find that BWA and the ones mapped with BWA and Minimap2 for the Nanobore data just differ by one site. The ones for the Nanobore data for the merged sets there's nothing in the BCF tools that, so the minimap mapped one compared to the VDOA mapped one. For the Illumina data map with minimap 2, it has one extra site compared to the BWA one, but the BWA has no extra ones compared to the minimap 2 mapped ones. So let's switch to the online server to look at this in more detail. Okay, so to continue on the server, what we're going to do is, firstly, we're going to look at our files that we had before. So we had ERR 999. These were VCF files. So we're going to look at what we have here. So you can see there for our VCF tools and BCF tools, we may have to check that they're compressed to the right level. So what we're going to do with each of these in this instance is I'm going to unzip them from the pre-compressed SAS they were before, so that they have the right level of, they're in the right format for our analysis. So we can check this by just looking at them all at the end here. So we've got VCF files here. So you can then use bgzip to look at the ERR9 .freebase.vcf and then do the same with the BCF tools one. And the next step then is to use Tavix. So Tavix indexes our files. We have to say that we are using a VCF file and then put the input there, ERR9.freebase, and then do the same for the other one as well. And that will index our files. The next step is that we can merge the mutation calls in each of these files using the isect function in BCF tools. So our first input is one of the files, let's say freebase, and then the other input is our other file, BCF tools, and then we have to specify certain parameters that we had before. And we're going to call our output, for simplicity, merge2.vcf. So that will look at the intersection. The mutations are present in both files, and we can check our output. There we have our header, and then we have our calls there as well. We can just check that we have that all those files together, and then we use var filter on that. So if you look at VCF utils, it has a function called var filter. Var filter is the name. Looking at depth of at least 10, at least 6 alternate alleles. We use our input of in.merge2.vcf, and our output is going to be in.merge2.filter.vcf. So we can look at our merged version, and we can see that there. So now what we can do is just count those mutations. So we can grep to count, ignoring any lines with a hash symbol on them. So it in.merge to anything. And you can see there that we had 25 after filtering and 29 before. And then we can look at the TS-TITV ratios of those files. So we look at stats, the stats function within VCF tools, and merge2.vcf at the initial version, and we're going to pipe it to grep.tstv. We see that initially we had 3.8, and then if we look at the one with the filter, we get 3.2 as it happens. And if we look at all the stats that are listed there, you see there's quite a lot of items there, which is why we're just focusing on the TSTV ratio for our purposes here. We can also look at the header lines of our VCF files. If we look at in.merge2.filter.vcf, you can see there's quite a lot of information there as outlined before. And things like DP are very useful for estimating the number of alleles that are present. SRF and SOR are also useful as our SAF and SAR. And if we look at an example here of a site, like the second one here, this one, you can see there we have a depth of 34, and we have how many alleles? SAR is 14, SRF is 2, SAF is 16, and SOR is 2. So that indicates this kind of 30 forward and reverse alternate alleles and 2 alleles that are from the forward reads and reverse reads for the reference. So it indicates a partial SNP that's nearly at fixation, but it may contain the reference allele at some low level. And then this SNP further up has a depth of 59, which is higher. We've got 22 reverse alternate reads, 36 alternate reverse reads, no reference reads, one for forward and one for reverse. So in any case, that's probably a complete fixed SNP. So now we can we've counted what's before. We can count the mutation type that's present. So if we look again at this file, we can count the number of using grep of insertions that are present, which is just 1. We can count the number of deletions. We can count the number of SNPs, which will be higher, 26, and we have just one complex SNP. If we were to look at that, we can just use grep to extract that complex mutation. Oh, that's not a complex mutation. So you might need to adjust those counts. Then we can use bgzip to compress that file in.merge2.filter and then index that with tabix as we did before. And now we can compare and contrast these different files to using the ISEC command we had before, BCF tools, ISEC, and then we had our in.merge original file, merge2.bcf, and then in.merge 2.filter file, and we're getting the ones that are different in BCF output. So what I need to do is compress that with bgzip first, in.merge to BCF. And if I try this again, it may give me an error because it's not indexed with tabix. So I have to use that tabix on in.merge to the BCF. So now it will work. If I put in the right command. Yeah, so you can see that that's where those sites differed between the unfiltered and the filtered version. So that's sites 21 and 217 for the start. So if we decompress temporarily in.merge to and scroll up to that site 21, yeah, we see there that depth was just 6. That's not going to be valid. That's a depth of 8, which is very, very low. And if we look at the other two, 241 and 27807, this 241 is a depth of 8, and 247, yeah, this is just a depth of 9. You can see that the other ones have a depth of that's very high, which is what you'd normally expect. So there's certain regions maybe that are pretty resolved here. So that's a kind of a brief overview of how we can go about a particle, and obviously we would want that to do that for many samples, and then also test more accurately the steps along the way to see what differed between the different samples. And one way of doing that is with BCF tools ISEC, where we can take our original command in, we're looking at the ERR9.bcf tools, so .vcf file, err9.freebase, and then we're looking at the consensus output for BCF. You can see that these are the mutations that were in the BCF tools that were not in Freebase. So there's quite a few there. You can see those three at the end I mentioned before. They're adjacent to each other. They're probably not real. And then vice versa, we can switch these around. And there you can see the ones that are in Freebase, which contain more structural variants that are absent in BCF tools. So you can see there's quite a lot at the ends again, which again are less accurately resolved regions. So now we'll move on to looking at it with IGV in our next video.